In the integrand's position, I do indeed have a proper rational expression, so partial fraction decomposition applies. Well, as long as I can factor the denominator. Let's see if I can. If it does factor, then the rational root theorem says that a rational zero, say r, is going to be of the form p over q, where p divides evenly into the constant term, q divides evenly into the leading coefficient. Leave me with these choices. So using synthetic division, let me see if I can find one that works. I found one. This means this third degree polynomial factors as such. X minus that zero. The quotient obtained upon performing polynomial division has coefficients down here. I can even do better. So let me bring that back. Now, more scratch paper. I'm going to decompose this one fraction into sum of two fractions. If that is one of the denominators, this is another denominator. This rational expression is indeed proper. So these two will be proper as well. This denominator is of degree 1, so the numerator could be as big as 1 degree less. That means it has to be a degree 0. That means it's just a constant. However, given that this denominator is a degree 2, this numerator can be as big as degree 1. I say as big as degree 1 because technically speaking, b might be 0. It might not be that big of degree. Eliminating fractions. Well, I think it's time to stop. At this stage of the game, I can do exactly what you did when you studied pre-calculus. I can go ahead and equate coefficients of x squared, of x, and equate constants. That's going to give me 3 linear equations and 3 unknowns. Now, you have some pretty sophisticated techniques for higher order linear system equations. Gauss-Jordan elimination on an augmented matrix. Rewriting the system as a single matrix equation and using inverse matrices. Or using Cramer's rule. If you don't mind, I'm not going to use any of those sophisticated tools. Here too, I'll be lazy in my usual fashion. If I were to equate coefficients, I could generate those 3 equations. But as my shortcut, as you saw in my last example, let me exploit this linear factor. Its 0 is positive 1/2. Now when I substitute that in for x on both sides, Look what happens on the right-hand side. This term completely drops out. I'm simply left with an expression involving a. That's just a constant. I'll be able to solve for I'm still plagued with a lack of board space. Now, I've run out of linear factors for which I can grab zeros, so I give up again. I'm simply going to now equate coefficients, but not writing everything out. If I were to equate coefficients of x squared on both sides of the equation, here it is on the left-hand side. On the right-hand side is a plus b. Excuse me. It's a plus 2b. And if I equate constants on both sides of the equation, I generate this. Now, that is a piece of cake to anti-differentiate. With this one, we need to finagle a little bit. If I'm going to commit to u sub, u will be its entire denominator, and du will be 2u plus 3. That constant is 3 times half the coefficient of x. So I'll make this constant 3 times half the coefficient of x. That's not legal. I added 3 to this numerator. I better compensate and subtract 3 from that numerator. You can double check my arithmetic. This plus this plus this is what I started with. Massaging that denominator a little bit by completing the square. In this fashion, I can now state the answer. Anti-differentiate term by term. But of course, you and I always want to make our answers look as attractive as possible. I can't do any better than that. Looks good to me.